Hello, I'm FRibeiro and I will present in behalf of Pedro Luis Almeida that performed this work for his master's degree under my supervision. And the work is called Machine Learning Applied to Urban Heat Island Intensity Prediction at the Metropolitan Region of São Paulo, Brazil. Urban heat island is a phenomenon related to urbanization that changes the surface characteristics and consequently the surface energy balance, causing surface and air temperatures in urban areas to be higher than for its surrounding non-urban or rural areas. The intensity of the urban heat island is determined by the difference between urban temperatures and rural temperatures. There is a difference between the surface urban heat island that considers surface temperatures and canopy urban heat island that considers air temperature. In this presentation, I will only refer to the canopy urban heat island. Urban heat island doesn't always indicate excess heat, but it may enhance heat waves and excess heat. Excess heat has several definitions, but it mainly means positive air temperature anomalies of short or long terms and should consider local typical conditions. Excess heat is frequently related to heat waves, and some researchers point to an increase in the frequency of heat waves in southeast Brazil. This austral spring-summer period brought atypically high temperatures, breaking records in São Paulo city. The excess heat caused an increase in energy consumption due to an enhanced demand for ventilation and refrigeration. Additionally, excess heat causes increased mortality, mainly due to strokes and cardiovascular diseases. And the urban heat island circulation may interact with other circulations and impact local weather. In São Paulo, under certain symptotic conditions, UHI interaction with the sea breeze circulation causes extreme precipitation, creating several problems for the citizens. Therefore, the present work aims to answer these three questions. 1. How intense is the UHI in São Paulo? 2. How is the air temperature distributed in the urban area? And 3. Is it possible to predict hourly urban heat island intensity in São Paulo with machine learning models? The methodological approach involved first comparing UHI intensity calculated by using operational stations to the urban heat island intensity calculated by using research stations. Secondly, using a cluster analysis to find stations with similar characteristics. And thirdly, developing machine learning models to try and predict urban heat island intensity. The study area is the metropolitan region of São Paulo, located at the Tropic of Capricorn, with 22 million inhabitants and an area of 8,000 kilometers square. To compare operational and research stations, we used an urban operational station in the city center, UOP, that was the closest one to the research operations, URES and USTR. We also used an operational and a research rural stations, ROP and RRES. UOP is located at the roof of a 15 meters high building. URES is a micrometeorological tower at the roof of a 77 meters high building, and USTR is at street level. The rural stations are not very close, but they have similar characteristics and are both south from the urban area and installed at the surface. We performed statistical tests to compare the temperatures and UHI intensity values distribution. The clustering analysis was performed for the 30 urban operational stations using meteorological and land cover data. Meteorological data was 10-minute averages of air temperature, relative humidity, and precipitation from 2009 to 2019. Land cover was represented by the percentage of built-up and the percentage of green infrastructure in an area of 500 meters of radius centered at the station. All the data was standardized using a standard scaler, A principal component analysis was performed and the clusters were determined by the K-means method. The optimal number of clusters was determined by using the elbow method, with the within cluster sum of squares. For the prediction models, data from the 30 urban and 1 rural operational stations was used. These are 10-minute average of meteorological variables from 2009 to 2019, resampled as hourly averages. The variables were air temperature, relative humidity, precipitation, atmospheric pressure, wind speed, direction, and gust. Wind speed and direction were transformed in zonal meridional wind components. Data was aggregated by cluster, and some other variables were created by feature engineering, such as cyclic variables to represent the hour of the day and the day of the year, lag variables to consider the previous 12-hour conditions, and mobile statistics, minimum, maximum, average, and standard deviation. We tested 3 models to forecast air temperature and urban heat island intensity for the next 6 hours. One was the ridge model, that is a linear regression that adds penalties to large magnitude coefficients. Another was gradient boosting, a decision tree-based method with an interactive boosting. And the last one, the multi-layer perceptron, a neural network-based method. The optimization of hyperparameters was performed by the successive halving technique. The models used recursive forecasting, and 70% of the data was used for training the models and 30% for validation. The validation metric was the mean square error, and a time series cross-validation was performed. Now for the results, the comparison between operational and research urban stations shows statistically different distributions, with the research station showing lower average temperatures than the operational. The street-level research station shows the highest temperatures, highlighting an influence of the height above the ground where the station is located. Despite the differences, the distribution curves have similar shapes. For the rural stations, the distributions are also statistically different, with the operational station 1 degree Celsius warmer in average. The distributions again have similar shapes. These differences impact UHI intensity calculations, with research stations showing an average of 1.7 degrees Celsius greater than operational stations. However, it is possible to affirm that the center of the city is in average at least 2 degrees Celsius warmer than its surrounding areas. Another relevant points are the occurrence of urban heat island intensities of 10 degrees Celsius or more, and an urban cold island. Therefore, operational stations may be used to forecast urban heat island. For the cluster analysis, using all the 30 urban operational stations, the elbow method resulted in 4 clusters, as shown by the figure on the left, with the within cluster sum of squares plotted by number of clusters. The figure on the right shows the spatial distribution of the stations divided by cluster. The red triangles are cluster A stations located from the center to the north, and clusters B in the blue square and cluster C in the magenta diamonds are almost surrounding the city center. Cluster D is composed by 2 stations on a transitional area from urban to rural and to the south of the urban area. We can see that these 2 cluster C stations are also in transitional areas, but to the north of the urban area. The yellow X shows the location of the rural station. Cluster A, the city center, presents higher temperatures, higher precipitation values, lower relative humidity, more than 50% of built-up areas, and less than 30% of green infrastructure. Considering the urban heat island intensity forecast models, Gradient boosting has the best performance, particularly for cluster C, followed by ridge and then multilayer perceptron. However, the mean square error is still relatively high for all the models. To further investigate the model performance, we took some examples of the gradient boosting model for cluster A that should present the highest heat excess. The top panel is the temperature for the urban cluster, the middle panel is rural temperatures, and the lower panel is the urban heat island intensity. Green dots are observed values and orange marks are model results. In this example, the model shows a good performance for the rural station that is in the middle panel. The observed urban temperature in the upper panel was lower than the previous day when it began to rise, and so the model underestimates the urban heat island intensity for the first 4 hours of prediction. In this other example, the urban temperatures on the top panel are better forecasted, but the urban heat island intensity is overestimated for hours 2, 3, and 4. Now for this last example, during the passage of a cold front, the temperature profile is completely changed, and we don't see the typical diurnal cycle. And since it is a less frequent phenomenon, the model cannot represent its characteristics. However, cold front passages are not events during which we are concerned about heat excess. To summarize our findings, for the first question, how intense is the urban heat island in São Paulo? The answer is the urban center is in average at least 2.1 degrees Celsius warmer than rural areas, but the intensity may reach 10 degrees Celsius. There is also record of an urban cold island. Street level temperatures may be 1 degree Celsius higher than in operational stations. For the second question, how is the air temperature distributed in São Paulo? The highest temperatures are found in the city center and to the north. Stations at the south are cooler. And the third, is it possible to predict hourly urban heat island intensity with machine learning? So machine learning algorithms show potential in predicting urban heat island intensity, particularly gradient boosting and during typical heat excess prone days. However, some other configurations and techniques should be considered to improve forecasting performance. I thank you and thank also the funding agencies, and I'll be happy to answer any questions.